Hi, my name is Steinar, and today I'd like to present the topic reinforcement learning. Uh, let's start with my references. I used a combination of articles. Some of them are from journals and others are from conferences. I found a book on reinforcement learning and I used Wikipedia, GitHub, and other websites. I used AI tools to summarize large amounts of text and to assist me in outlining the project and to generate images. This presentation is also based on a project I worked on at Leiden University in the Netherlands a few years ago. So what is reinforcement learning? Imagine learning to ride a bike. You would be the agent on this diagram. First, we take action in an environment by trying to pedal. Sometimes we stay upright, which in itself is a positive reward. Sometimes we fall. We adjust our balance based on what worked. And with enough trial and error, we eventually master it. We act, experience, learn, improve, and repeat. Reinforcement learning has evolved a lot in recent years. It kind of began in the 50s with Bellman's dynamic programming work, establishing the mathematical foundation for RL. The 80s, we got two key developments. First, researchers began connecting these mathematical ideas with how animals learn through trial and error. Second, we saw the introduction of Q-learning by Watkins in 1989, which became one of the fundamental algorithms we still use today. The true revolution came in 2013 to 2015 when DeepMind combined deep neural networks with RL, creating DQN. Their system learned to play Atari games from scratch just by looking at the pixels on the screen, reaching human-level performance on many games. This was revolutionary because it showed that the reinforcement learning could work with raw sensory input and not just carefully engineered features. Then in 2016 we had what many consider the field's defining moment. AlphaGo defeated the world champion Lee Sedol at Go, a feat that many thought was decades away. This wasn't just about winning a game though. It demonstrated that reinforcement learning could master tasks requiring long-term strategy and intuition. The field has come a long way from its theoretical beginnings, and it's exciting to think about what the next breakthroughs might be. The Markov decision process contains the core components of reinforcement learning environments. Let's break it down using something we're all familiar with, a game of chess. First, we have states. Think of this as a snapshot of the current situation. In chess, it's simply where all our pieces are on the board right now. States must contain all the information you need to make your next decision. That's what we call the Markov property. It's a fancy way of saying that the past doesn't matter, only the present state. In chess, you don't really need to know how the pieces got to where they are to decide your next move. Then we have actions. These are all the moves you can make from your current state. In chess, that would be all legal moves at that moment. Now, the transition probabilities tell us how likely we are to end up in different states after taking an action. In chess, this is deterministic, of course. You know exactly where you'll end up. But imagine a game where you roll dice, now there's probability involved. Rewards are how we know if we're doing well. In chess, capturing a piece might give you a small reward, while a checkmate gives you a big one. Finally, we have the discount factor, which is like telling your agent how forward thinking it should be. A low discount factor is like a player who only cares about capturing pieces right now, while a high discount factor is like a grandmaster thinking several moves ahead. All these components work together to create what we call the Markov decision process, which is the mathematical framework behind reinforcement learning. The gymnasium, which was previously known as OpenAI Gym. It was discontinued by OpenAI, but it's currently maintained by the Farama Foundation. It's a fantastic learning resource and a Python library. It's essentially a collection of virtual playgrounds where you can test and develop RL algorithms. What makes it special is its simplicity. Every environment follows the same basic pattern. You can start a new episode, take actions, and get feedback. Whether you're teaching an agent to balance a pole, land a lunar module, or play Atari games, the interface stays the same. With this standardization, once you write an algorithm that works for one environment, you can easily test it on others. Here we have a simple Python example using the Gymnasium library. It initializes an environment, in our case the lunar lander. There's a main loop that runs for every action we take. In this example, we're randomly selecting an action. We need to replace that with a more sophisticated method. For every action taken, we get the state, the reward, and whether the episode has terminated, along with other details. If it's terminated, we just reset the environment and try again. One of the most popular environments in the Gymnasium is the lunar lander. Imagine you're at NASA trying to land a spacecraft on the moon, but you get to practice in a simulator first. The challenge is quite straightforward. You start at the top of the screen with a lander that's affected by physics and a random force, so no two runs are the same. Your goal is to land safely on the designated pad without crashing. You have 4 possible actions at any given time. You can do nothing and let gravity do its thing. You can fire the main engine or use the left and right thrusters to control your angle. The environment tells you everything you need to know about your lander: where it is, how fast it's moving, which way it's pointing, and whether you've made ground contact. This is an 8-dimensional vector we call the observation space. Then there's a reward system. It's like a video game score. You get points for doing things right, like touching down gently or landing on the target, but you lose points for wasting fuel or crashing. The goal is to maximize your score by landing efficiently and safely. Now onto the learning process. Think of Q-learning like learning to cook without a recipe. You try different things and remember what works. It's essentially a scorecard for our agent to track how good each action is in different situations. Starting with zero knowledge, the agent builds experience through hundreds or thousands of attempts, updating its scorecard of Q values based on rewards received. The agent uses an epsilon greedy approach. It's mostly doing what's worked before, but occasionally trying something new. This balance between exploitation and exploration is the key to learning. Over time, the agent develops a kind of intuition, knowing exactly what action will work best in any situation. The formula you see shows how these Q values get updated with each new experience. Deep Q learning represents a major breakthrough in reinforcement learning by combining traditional Q learning with neural networks. It's like upgrading from a simple lookup table into a sophisticated pattern recognition system. Instead of trying to memorize every possible situation, the neural network learns to recognize patterns and generalize from experience, like a human pilot would do. What makes it work are 3 clever innovations. It uses experience replay, storing memories of past attempts and randomly revisiting them for learning. Then it uses a separate target network that provides some stable learning goals, preventing the agent from chasing its own shadow. Finally, it learns from multiple experiences at once through mini batches, making the learning process more efficient. Here we can see our agent in action, successfully landing the lunar module after training. But how does it make these decisions? Let's look at the neural network that powers it. This network is the agent's brain. On the left, we have 8 input neurons that receive information about the lander's current state, where it is, how fast it's moving, etc. It's like the sensory input a human pilot would use to land a spacecraft. These inputs feed through 2 hidden layers, which you can think of as the network's thought process. The connections between these neurons are like decision-making pathways, each with different strengths or weights. They have adjustable dials. It's similar to how a human pilot develops instincts about when to fire the engines based on experience. Finally, on the right, we have 4 output neurons, each representing the Q value for a possible action: doing nothing, firing the main engine, or using the left or right thrusters. The higher the Q value, the more promising that action is in the current situation. Through thousands of attempted landings, the network gradually adjusts these weights through deep Q learning from both successes and failures until it can reliably choose the right action in any situation. Our neural network learns through gradient descent. Think of it as learning from mistakes. Each landing attempt teaches the network something new. First, our network makes a prediction. Maybe it thinks doing nothing is the best action when near the ground. Then we see what happens. If the lander crashes, that's a big negative reward. Imagine our neural network's weights as thousands of tiny dials that we need to adjust. But which way should we turn each dial, and by how much? That's where gradient descent comes in. It calculates the slope or direction for each dial that will reduce our error. It's like having a compass that points towards better predictions. Here's a concrete example. Our network confidently predicts doing nothing is great and gives us a Q value of 0.9. The lander crashes, revealing that this was actually terrible. True value closer to -1. Gradient descent measures this large error and calculates precise adjustments. The weights that strongly contributed to this mistake get adjusted more significantly. This process repeats thousands of times across all possible situations. With each iteration, our predictions get closer to reality, until eventually our lander knows exactly when to fire its engine and land safely. Now let's see how reinforcement learning is making real-world impact. In energy, RL is used to optimize power grids and to control magnetic fields for nuclear fusion research. For machine control, it's used in Google stratospheric balloons navigation, manufacturing robots, NASA drone landings, and self-driving cars. Financial institutions use RL to develop adaptive trading strategies. Gaming provides some of the most visible successes, with AlphaGo defeating world champions and OpenAI 5 competing professionally in Dota 2. Spotify refines its music and podcast recommendations using RL. It's learning from your interactions to improve suggestions. And while it's not officially confirmed, experts believe that SpaceX used the reinforcement learning simulations to develop the impressive self-landing capabilities of the Falcon 9 rocket boosters you see here. What's exciting is that we're just beginning to tap into reinforcement learning's potential for solving problems where traditional programming approaches cannot compete. Thank you.